Okay. Good afternoon to everyone. Just come in because here we have heating. Outside is no heating. Sorry? Okay. Para? Silence, please. Okay. Welcome to the third session. I appreciate very much the invitation from Maite, Jose, Elisenda, all the organization committee, and I am very proud to be here because here I have many friends and colleagues. Then in this session, we have 4 papers that deal with energy policies and regulation and how they impact on several performance variables. That it's very interesting to know how the public incentives and other type of instruments could improve some important measures as electricity prices or the transition of the companies to the transition to greener economy or whatever experiment related to how the prices could be moved ups and down. In these four papers, 2 of them, the first and the fourth, deals with Spanish data. The first one is estimating the impact of grid limitations on electricity demand reduction and renewable targets in Spain. The speaker will be Daniel Davi-Arderius. He's chair of the energy sustainability, and the paper tries to assess the potential impacts of reduction in electricity consumption and increases in renewables connection on the redispatching processes. They use Spanish hourly data from nominated electricity market operators, and they control for several robustness, dynamics, and endogeneity. The second one paper is about regional environmental and energy policies. Are they effective for the sustainable transition of listed companies? And the presenter will be Maria Gaia from University of Parma. And the study tries to assess the effectiveness of regional environmental and energy policies using data from listed firms, Italian listed firms, and using a propensity score matching, right? And the third one is about the effects of carbon taxation on electricity price dynamics, empirical evidence from the Australian market. The speaker will be Nicola Comincioli from Universidad of Brescia, and the study tries to investigate the impact of carbon tax on the national electricity market using the Australian market and how the introduction of carbon pricing mechanism moves the dynamics of electricity price. Okay, and the fourth paper is about leakages from fuel taxation, evidence from a natural experiment, and the presenter will be Jordi Teixidó from Universitat de Barcelona, and the paper deals with the analysis of potential carbon and revenue leakages when border countries implement different carbon energy taxes using Spanish transport sector and in the period 2011-16. Okay. The floor is yours. We will organize the session. Just first, all the speakers will present, and then we collect all the questions, suggestions, comments briefly, because we have some time. Thank you.
Okay, thank you very much for being here and for inviting me to present this paper. First of all, I want to send a special greeting to Juan Rosellón. Juan could not be here physically, but he will be present with this paper, and because he is one of these co-authors, also with Tim Skytecade from the MIT. Okay. This is the outline of this presentation. We'll see the introduction, aims and hypotheses, literature, the data, results, and conclusions. Okay. So this paper falls in the scope of the ongoing European crisis related with the Russia invasion of Ukraine, where the European Union proposed to reduce the gas consumption. And the European Union defined two main targets to achieve that. One is reducing the electricity consumption, and the other one is to connect renewables. At the end, both ideas had in targets to reduce the gas consumption. Okay, however, as you will see in this paper, some of the market outcomes, some of the day-ahead energy schedule we have from the market could not always fit with the physical characteristics of the networks. Due to the need to fulfill some operational constraints, in consequence, grid operators should do what is known as redispatch. Redispatch is changing some of the market outcomes from the schedule, generation, and consumption in order to ensure the fulfilling of some technical criteria. So the aim of this paper is to analyze the impact of connecting more renewables and reducing the gas consumption, specifically related to the redispatch processes of combined cycle. We want to know if when we connect more renewables and when we decrease the consumption of electricity, we want to check, our hypothesis is that the gas consumption associated to combined cycle increases. Increases not because of the day-ahead market, but to the need to redispatch these plants to ensure some operational criteria. We use Spain. Spain is a quite excellent case because it's an isolated country, very small cross-border capacity, and this paper falls very well with what this morning Mark has explained us, the operational cost. So we are going deeper in the operational cost that this morning Mark has explained us. Okay, just to put in context how the redispatching processes are going, we have, first of all, number one, we have the economically efficient program. This is what the market provides, the economically efficient assignment of consumption and generation. However, grid operators must always ensure that this program can be allocated in the system and that is feasible. If it's not, they should change some of the nominations from the market. This is known as redispatch. So the combination of both points at the end, number three, we have the economically and the technically feasible program. After that, we have the intraday markets, which are out of the scope of this paper. Regarding the literature about these processes, redispatching, the impact of grids or renewables on grid congestions, there are some empirical, some theoretical analysis. Regarding the redispatching processes, there are not many empirical analyses. This morning, I should add the paper from Mar, because it's another one that should be included here. And one of the paper related to redispatching is the one we published last week about with Tim, where we try to analyze, not in this way, but we analyze what is happening in the redispatching processes in Spain, more focus on the environmental impacts on the CO2 emissions. This is the paper we have written to analyze the problem. So this is the second stage of this paper. Because what is happening in Spain is that redispatching, as Ester clearly explains, redispatching processes are mostly activated not to solve congestions, but to solve voltage problems. This is very relevant because this, as you will see in our empirical results, the redispatching needs increases not when the consumption increases, but when the consumption decreases. This is what is happening in Spain, and this anticipates what could happen in other countries. And because at the end, the technical problem is that when we have a lot of wind production or solar production in the system, we need to start some synchronous generators, in this case, combined cycles or coal plants. To put in context and to put some numbers on the table, here you have 3 columns, 2019, 20, 21. You have the annual consumption, to 250,000 gigawatts. You can see that combined cycle covers between 10 and 15% of the annual production. However, when we look in another table, you see that redispatching energy that is part of this annual demand is between 2, 3, 5%. And if you look these 7,000 gigawatts, you can see that the one that comes from combined cycle is about 4,000, more than 4,000 gigawatts should be connected, and another 1 megawatt should be disconnected. So depending on the problem, in some cases, they should start or should decrease. To put this in context, it means that between 7 and 23% of the gas consumption from this technology comes from redispatching processes. So this means that it's important to see what is happening in that if we want to reduce the gas consumption in the country. If we analyze graphically, in the vertical axis, you can see the redispatch energy from combined cycle. You see that this decreases in average when we increase the sum of electricity consumption. This is why I explained before, we have not a congestion problem, we have a voltage problem in the grid. And they also increase when the participation of wind and photovoltaics increase in the system. Both technologies are made of power electronics whose performance is not the optimal. So this is why the grid operators, in this case the TSO, should upward more combined cycles. The data we are using comes from the NEMO, the Spanish NEMO, and well, we use the redispatch energy. We compare the market program and the program after the redispatching processes. In this paper, we use four variables. We use, first of all, the economical efficient market schedule energy, the aggregate demand for each hour. We include the share of renewables in the previous energy efficient market schedule, and the upward combined cycle energy. This is the energy that should be upward started. And finally, the net redispatch, which is the difference between the upward and the downward. Let's go to see the empirical analysis. And the empirical analysis, we used a time series analysis. We differentiate variables because of stationarity. We include the lack of our endogenous variable to capture dynamics. And we try to see how this redispatch energy is explained by the scheduled energy in the market and by the share of renewables. We use maximum likelihood estimations. Let's go to the preliminary results. I think this is the most interesting thing for you. I will show just the net redispatch energy because I think this is what affects the gas consumption. We see that when we increase the scheduled energy in the system, the total energy consumption in the system, the combined cycle energy from redispatch decreases. In other words, if we try to apply the European policy to reduce the gas consumption, to reduce the electricity consumption, we will increase the gas from another way related to these processes. And the same from renewables. When we increase the share of renewables in 1 percentage point, we also increase the needs to start combined cycle and the need we can transform these megawatts in gas consumption. To put these numbers at the end in gas, because we can transform megawatts in gas, what we have been doing, we have for each of these years, we calculate which one could be the 5% savings for the 4 peak hour, as the European Commission says. We calculate what could be the theoretically savings in electricity consumption. In theory, this, the first and the second row. However, this decreases, but we have a trade-off with some combined cycle that should be started. So the most relevant conclusion from this slide is that if we reduce 1 megawatt of consumption to decrease the combined cycle production, we are not decreasing 1 megawatt, but only 0.935, 0.96. So the efficiency of this policy is not 100%. We have some trade-offs related to the operational of the system. And in the second case, we use the coefficient related to renewables, and we try to estimate the same. What could happen if in Spain we connect all the scheduled or the planned renewables, wind and solar, and we also see that gas consumption related to this technology will increase. So, as main conclusion, we dispatch energy in combined cycle. This is the gas consumption associated to that increases when we have more renewables and when we decrease the electricity consumption. So the European targets should consider these operational constraints from our point of view. And as final conclusions, we consider and we explain that when we have a highly decarbonized power system, when we have a lot of renewables in the system, we always need some synchronous generators, we always need some combined cycles running to control this problem. We have seen in the literature some common cases also in the UK, so this problem is from Spain, but we have seen some papers that already advocate some of these similar problems in a preliminary stage in the UK. So the operation in highly decarbonized power systems at the end have some efficiencies, and these results show that what we are finding here is the short-term impact, because at the end we should have in mind that the TSO is always commissioning new assets, new cables, we are connecting new renewables. However, we see here a trend. And as policy recommendations, the main question could be, well, what can we do? Can we solve that? Yes. So we can solve that. There are solutions, not easy. But these inefficiencies should be solved. And they can be solved creating a specific ancillary services. The idea is that renewables should be able to control the voltage stability to the system. This is, well, theoretically it can be done. However, this requires some operational cost for renewables. This is why we propose in this paper and in the previous paper to create a specific ancillary service to compensate the renewables in order to avoid curtailing them and to connect a lot of combined cycles. And another policy recommendation at the end is considering where we locate renewables, because we can locate renewables considering the best optimal weather conditions, but we also should consider what is the optimal location considering the grid operational. And here we can several proposals: smaller bidding zones, locational incentives in future renewable actions, or regional use of system charges. And finally, as this is an ongoing work, next steps we have in mind and we are working, we want to analyze if these coefficients remain constant in the peak and off-peak time. We suspect that there might be some differences regarding what may happen with combined cycle. We want to analyze that. We want to link our findings not only with reducing the electricity consumption in some hours, but to energy efficiency, to self-consumption, at the end to any policy that could change consumption. Because if we are finding, in this case, that reducing the consumption produces that, any policy that could change the consumption might create some needs to consume gas. And we want to analyze, finally, potential trade-offs between the need to redispatch, gas consumption, grid expansion, and the process to connect new renewables. So we are working in these three ways. And thank you very much. At the end, we can answer questions.
Thank you, David. Now we move on to the next speaker, Ms. Maria.
Climate change is a global phenomenon. Its effect differs from place to place. Therefore, a strong policy response is required not only at a global level, but also at a local one. Local authorities, and especially regions, play a key role in this context for different reasons. First, because regions are closer to citizens and enterprises. Second, because regions understand local vulnerabilities. And finally, because regions have great expertise in environmental and energy policies. But concentrated focuses on the local level, regions are not alone. There are also other important actors that play an important role, and I refer to local enterprises and especially to the big enterprises. Because big enterprises and especially listed firms are so important, because they are often leader in the market, and for this reason smaller firms and especially small and medium enterprises follow the example and the behavior of larger firms. In this context, we try to investigate how regions and local and large enterprises can act together at a local level in order to react to the energy transition. As a larger firm adopt voluntary policies, green, environmental.
This one?
Okay. Environmental and energy policies, often voluntary environmental policies can coexist with regional policies. However, a systematic study on the interaction between regional compulsory policies and local and voluntary firm-specific policies has not been investigated yet. And we try to fill this gap. Oh, no. Okay. And for this reason, the aim of our paper is to examine the effectiveness of general policies for reducing air emissions, renewable energy policies, and energy efficiency policies on a sample of Italian listed companies in the period from 2008 to 2019. Italy is a very interesting context in this field for different reasons. First, because Italy is a great emitter of greenhouse gases in the European Union. Second, because Italy shows strong regional differences. And finally, because there are in Italy a lot of small and medium enterprises influenced by larger and listed firms. Previous literature shows that subnational authorities play a key role in promoting the green transition at a local level. Specifically, Cohen and other authors in 2021 find that regions can be really agents of change, as they demonstrate that they can enhance the effectiveness of renewable energy and energy efficiency policies. Although previous literature showed the very important role played by regions at a local level in order to promote the sustainable transition, so far the specific role of regional policies in influencing the green and energy transition of firms has not been investigated. We therefore try to test these hypotheses. Regional environmental policies boost the green transition of firms. Regional renewable energy policies boost the energy transition of firms. And finally, regional energy efficiency policies boost the energy transition of firms. But as I've said before, regional authorities coexist with other local actors. And a single public policy could not be always sufficient to stimulate the green and energy transitions. The effectiveness of policy mix in renewable energy depends on several firm-specific features, and previous literature shows that firm size is one of the most important in this field. Despite the importance of the policy mix between regional policies and firm-specific voluntary policies, no studies have so far investigated the effectiveness of these two kinds of policies when they work jointly. For this reason, we try to investigate other three hypotheses. And specifically, we investigate whether the policy mix, that is regional and firm-specific environmental policies, boost the green transition of firms jointly. And also in this case, we tested the different kinds of policies. Specifically, our sample consists of 63 Italian-listed firms selected from the universe of Italian-listed companies from the period 2008-2019, and these listed firms are located in 10 Italian regions. Firms' environmental performance indicators are extracted from Refinitiv data stream asset 4, and we use three performance indicators: CO2 equivalent emissions, the emissions category score, and the environmental pillar score. The emission category score is a score ranging from 0 to 100 that measures the efforts in reducing emission by firms, while the environmental pillar score is a sort of environmental rating, a global indicator of the environmental performance of the company. We consider 3 types of policies in our study: general policies for reducing air emissions, renewable energy interventions, and energy efficiency measures. And these 3 kinds of policies are implemented and studied both at a regional level and both at a firm level, because we extracted information on regional policies by the database by ISPRA. This is the Italian Institute for Environmental Protection and Research, while firm data are extracted from Asset 4. Okay. Go fast through the methodology. We estimate the average treatment effects following the 3 pairwise comparison: regional policies versus no policy, the policy mix versus regional policies, and the policy mix versus no policy at all. Let's move from the result. We follow a 2-step analysis. First of all, we estimated using a multinomial logistic regression the propensity scores. In this table, we can see that per capita GDP is the most relevant macroeconomic factor explaining the adoption of all our policies by Italian enterprises. The unemployment rate has mainly instead a negative effect for the implementation of energy policies. The specific impact of firm characteristics, that is liquidity, profitability, and size, vary according to the type of policy. In the second step of our analysis, I show the estimate of the average treatment effects. The first analysis is referred to the multiple treatment effects of environmental and energy policies on CO2 emissions. And looking at this table, we can see that if we concentrate on general policies for reducing air emissions, regional policies are effective, but the policy mix is not effective as the coefficient is negative. On the contrary, if we concentrate on the renewable energy policies, we can see that both regional policies but also the policy mix are effective in order to reduce CO2 emissions. Moreover, we test the multiple treatment effects of environmental and energy policies on the emission category score and on the environmental pillar score. The results are quite similar, so I comment both together. In this case, results are completely different because regional policies alone are not useful in order to improve the emission category score, but also the environmental pillar score. On the contrary, the policy mix, that is regional policies and firm-specific policies, appear useful and that is effective in order to improve both the emission category score and the environmental pillar score. Finally, our conclusion and policy implication, our results show that when we deal with environmental and energy policies, there is not a one-size-fits-all approach. Specifically, in some cases, regional policies alone are enough to boost the green transition, but in other cases, a policy mix is required in order to have interesting environmental outcomes. The policy mix seems sometimes a win-win strategy in this context, and for this reason, I think that these results suggest that cooperation between public and private sector has to be improved in order to promote the sustainability transition of firms. That's enough. Thank you.
Okay, thank you, Maria. Now let's move to third paper from Daniel. Let's see. Sorry, Nicola. This one, Daniel, regional. There's only 3 here. Okay.
Okay, perfect. Do you hear me? No. Hello? Try again. Test, test. Does it work? Otherwise, okay. I was trying to increase the volume, but it was a wrong moment. Okay, so here we are. Thank you very much for being here to attend my presentation. My name is Nicola Comincioli. I am a researcher in economic policy in University of Brescia and also at the Fondazione Enrico Mattei in Milan. Today I'm glad to be here to present you this paper, joint work with Professor Sergio Vergalli and Mattia Guerini, also from University of Brescia and FEM, in which we are going to, as from the title, investigate with an empirical exercise what happens to electricity price volatility when a carbon tax is in force. We do this empirical exercise based on the Australian market for a reason that I'm going to explain in a couple of slides. Well, this is the outline of my presentation. I will start with an introduction in which I'm going to describe the context where the study is based and try to explain what is the motivation of the study and what is the gap that we are intended to fill in the literature. Then we'll spend a few words about the theoretical model. Nothing new, but we use different techniques at the same time to follow our ideas. And then I will spend most of time on the empirical result. I will detail some facts about the database we use. Most importantly, I will describe the result of the estimation of the 2 models we use. Finally, I will try to draw some conclusion and some implication, especially in investment policy. Okay, let's start with a brief introduction of the context. We're talking about Australia, and here the national electricity market, also called the NEM, was established in 1998, and nowadays it serves more or less 90% of national consumption and serves the eastern and southern states of Australia. There are 5 states served by the NEM that correspond to the 5 regions. Each region is interconnected to the other, making the NEM the longest interconnected power system in the world. The authority in charge of managing the national electricity market is called the Australian Energy Market Operator, that both manages the natural gas and electricity market. We are low in battery. Okay, here we are. The NEM is a market very peculiar, very modern. It was established, as I told you, in 1998, but is very efficient. It is a wholesale market where more or less 400 operators are active. By operators, I mean generators, retailers, sellers, and whatever, making the market with a high level of competitiveness. consider just a very high barrier to enter this market, but despite this point, the Hirschman and Findel index ranges between 25 and 30% since 1998. That for this kind of market is pretty efficient. What is the problem about this market? The big deal is that it is very reliant upon fossil fuels. I can't read, but if I'm not mistaken, the 71% of electricity in 2021 was generated by brown sources, and this is one of the highest share within the developed economies. This happened for two reasons. The one is very easy. Australia is a country which is very rich in natural resources, especially coal. Coal itself accounts for 65% of national production of electricity, and this is the basic one. In addition, we can see the cause in the package of legislation that established the NEM, that in the 90s, so in a time where when the sensitivity about climate change was completely different from nowadays, this package of legislation had the efficiency and the competitiveness as the only overriding priorities. So the cheapest source was the only option to use. Luckily, the sensitivity of the government about the thematics of climate change and climate risk changed through the time. And in 2011, we had a milestone in Australian effort to mitigate the emission with the Clean Energy Act. This is another package of legislation enacted by a minority government in 2011 that had a different goal in terms of mechanism in order to reduce emission. The most important one is the carbon pricing mechanism that basically introduced in Australia a carbon tax. We are talking easily about a carbon tax because it was, these laws introduced a carbon permits to be bought by companies polluting more than a specific quantity, available at a fixed price and with no limiting quantity. So basically it is a Pecunian tax aiming to recoup the environmental damage of emission. The answer to the question why Australia lies exactly here. Because the government was a minority government, it did not last very long, unfortunately. And the consequence is that just after just 2 years since the enforcement of the carbon pricing mechanism, the following government repealed it. So Australia represents a unique case where we can use data about the developed countries in order to study both the effects of the introduction and of the repealing of the carbon emission measure. In this plot, I'm showing you 6 years of data regarding the log prices and log volumes of electricity in New South Wales. Recall that we have 5 regions. I'm going to show you just some results here and there, but they are pretty robust across states and across time series. What do you notice is that we have clearly 2-year period. Okay, I didn't tell you, 6-year period, 2 years before carbon tax, 2 years, gray shaded area with the carbon tax in effect in force, and then 2 other years. What we notice is that in the middle we have a complete sudden break that is completely deleted at the end of carbon tax. We have an obvious increase in the mean, for sure, because even if the market is pretty competitive, part of the price of the carbon tax is paid by the final customers, and so we see an increase in the mean. But most importantly, we see a different behavior in volatility. That is the focus of our study. We noticed 2 things at least. First one is that the height of the spikes is much higher before and after the carbon pricing mechanism. And consider that this plot is expressed in logarithms. So in reality, the difference is much bigger than depicted in this figure. First point. Second point is that we can try to imagine that in over time series, regardless of the carbon pricing mechanism, we have some period of time where things work normal in some sense. We have regular behavior, but sometimes this regular pattern breaks and we have sudden spikes. We can imagine it like a normal low volatility state of the world when, I don't know, for example, the demand is easily satisfied by the supply, we are not close to the limit of the system, but sometimes when this condition of normality comes down, we have a break in volatility. So we observe these spikes. A very interesting thing is that this situation of high volatility are less frequent and with a shorter duration during the CPM. So we are not making any causal statement. We are limiting to observe that under the CPM, the price of electricity behaved in a completely different way. And this is basically the motivation of our study. We want to investigate this phenomenon in order to provide useful information to those, widely speaking, category of investors that make decisions based on electricity price. and on electricity price volatility. Consider, for instance, electricity as an exogenous factor in macroeconomic models, or a field which is much more common to my research activity, real option model. In real option theory, we are an agent, economic agent endowed with the option to start up a company where our profit is linked to a source of uncertainty, that may be electricity price. So knowing that under some condition electricity price behave differently could provide very, very useful information to all those subjects that makes investment decisions. Okay. The methodology is, we use is dual. The core of a paper is the second, the last bullet you see in the slide. But we decided to run a preliminary operation because electricity data are pretty peculiar. What do I mean by that? It is well known that there is a strong periodic structure within electricity data. We know that every day we have a peak in demand at the very early morning, at the afternoon, in the middle we have a minimum, and the minimum of all day is more or less at 2 a.m. So we have deep knowledge of the cycle within data from the daily frequency to the yearly frequency, during the summer or during the winter. All this kind of stuff. So we want to try to avoid, to remove all this information, all this detectable information, to provide a series of prices filtered of seasonality in order to reduce the distortion induced by the presence of cycles, and then study the volatility structure. Okay, I'm assuming that I'm late, so I'm just going to spend a few words about the model. Okay, what is the idea of the time series decomposition? A time series can be split in different components, and this component can be added together, multiplied together. We have different options. Here we decided to adopt a building block approach, where a time series YT is seen as the sum of a long-term trend of a set of short-term flickers plus phi t, which is the harmonic component, which is the component I'm going to explain in a couple of slides, that accounts for imagine it like a composite sine wave, where each sine wave is a specific frequency, the daily, the monthly, the yearly, and so on. The long-term trend and the short-term flickers are pretty easy, so I can skip if I... Okay, just a third-order polynomial of time to allow the presence for inflection points and a set of dummy variables for day of the week and for holidays effect. Here is the most interesting thing of this part of the model, the population spectrum. It is a function basically of autocorrelation within time series, which is borrowed from signal processing theory, that allows to detect at which frequency there is a cycle recognizable within data. At this point, I can just tell you that this function hits a high value in its exact correspondence of a frequency where we have a cycle. But I'm in rush. Here is the explicit form of the equation where all the components have been plugged together. But imagine to have real data. We remove all the seasonality we can account for, and we have some filter residuals. Now this is, it enters in the game the Markov-Zwicky model. We assume that the residuals are drawn by this first-order autoregressive model, where, if you notice, the autoregressive coefficient is not state-dependent, while the intercept, that is the unconditional mean, and the variance are both state-dependent. What does it mean? It means that we allowed the mean and the standard deviation to vary according to a state, which is driven by a variable we do not observe, but we can infer. Okay, and here let's go to the empirical result. A couple of words about the dataset. The Australian Energy Market Operator provides beautiful data with sample with half-hourly frequency for all the regions since 1998, so we can really have fun about data. We made some standard preprocessing and work with logarithm. And this is the counterpart of the first plot. We already see from the basic summary statistics the effect that we have a strong difference in mean and in variance. But let's go to some interesting result. This is the population spectrum. This is the function whose spikes represent a cycle. Maybe it's not very easy to recognize, but if I look closer, I have put a little arrow over the spikes. The spikes correspond to a specific value on the domain of the function that can be interpolated and transformed in a frequency. And the nice thing is that we have prices on the left, volumes on the right. The spikes occur exactly at the same frequency that are summarized in this table. Okay, Okay, not all series are as easy to Victoria, for example, to be analyzed, but the result here is that we are able to detect some meaningful cycles within data, and the detection appears at the very same frequencies. That makes sense. The one-day frequency is the most interesting that occurs for every time series we analyzed. The other one, maybe, electricity price can be very volatile, so it's not always easy to recognize and prove the presence of a spike, but more or less we are here. This information is used to build the harmonic component that, together with all the other items we used, allow us to draw this plot. They are the 4 components of a time series. First one is long-term trend from top left clockwise. The harmonic component that from the plot is not easy to recognize, but is a composite sine wave, so from a very short length wave to the very long, and the dummy variable representing the day of the week and holiday effect. Here there's nothing especially new in the last 2 plots. The regression is very significant, more or less 20 to 26 regressions have been used in each estimation, but the results are acceptable at least. Okay, and this is the core of the paper. This is the result of the fitting of the Markov switching model. Okay, now I realize that I put too much information in this plot, but just focus please on the first bunch of columns that represent the result with no control variables. Results are robust in any case. The first set of rows represent the low volatility state of the world. Below we have the high volatility state of the world. Sorry, but I can't read at this distance. Where is it? Okay. So what do we notice here? Here we notice that the gray shaded areas are all the coefficient significant at 5% interval of confidence. So the model seems to work. And here we prove that when the CPM is in force, the mean is always higher in both states of the world. The volatility is always lower in both states of the world, and if we look vertically, in the high state of the world, that I recall at this point is just a label we put on it, the volatility is always higher. So it makes sense to imagine this framework to describe the data. And this is the first part of the result of the Markov switching model. We estimated significant coefficient to describe these dynamics. Okay, and more or less on time. The last result is this one. This plot represents the inference about ST. ST is the unobserved variable that represents the state of the world. Again, the gray shaded area represents the period of time in which the carbon pricing mechanism was in force. As it is easily to see that the occurrence of events of high state of the world is higher before and after the carbon pricing mechanism, while during it was much lighter. And we have a hint of this phenomenon also from this result. It's maybe again difficult to read, but we have 9 square matrices that are called the transition matrices that collect the probability of being in the state I at time 0 and being in the state J the following time. Here results are more mixed, but at least we found a strong evidence. We see that it's more difficult to switch from the low volatility to the high volatility state. So again, it is half of the proof we were intended to find, but again, this result shows that in some sense it's more difficult to go in the high volatility state. And if we read this as not as a consequence, but as a phenomenon observed under the CPM, we can say that under the CPM, if you are in the low volatility state, it's more likely that you remain there. The bad news, I have to be honest and I have to say, is that is also longer the expected duration of the high volatility. But since it's less likely to be there, on average we earn something. Okay, we have different ideas to develop this paper for the future. I'll be more than happy to answer a question or describe our future step later. At this point, I would like just to stress what is our goal. Our goal is to provide information to those subjects that make investment decisions. And price of electricity, especially nowadays, is pretty important as a source of uncertainty. So thank you very much for your attention, and I'll be more than happy to answer your question later, after the presentation or later. Thank you.
Thank you, Nicola, and sorry for the... Okay, now let's move to the final presentation.
Hello, hello, hey. Hello, everyone. Thanks to the scientific committee and to the organization for allowing me to present our piece of research. I'm always very happy and very excited to be able to do it. So this is a joint paper with Xavier Lavandeira and José Mari Laveaga and Francisco Palencia. I'm Jordi Teixidó from Universitat de Barcelona. I share building with this great organization, not the same floor, but we share the building. Not this building, unfortunately, but also a cool one. And I'm going to talk about leakages. Leakages mainly from carbon leakages, and of course, as well, some revenue leakages, as Esther already mentioned. This is a working paper, so comments are very welcome, and I'm presenting it as in the way it came out. So somehow this is how results appeared, so this is how I'm presenting them. So I'm responsible here to do a smooth transition towards transportation sector, so then let me just contextualize a little bit the problem here. So, yeah, I thought I would see it better here, but not that the case. So yeah, emissions from transportation represent a very big share of emissions, and actually I have, because I had to send this before, and I always check the slides just the day before. I was not allowed here, so I decided to put everything, the sentences and the images. So here you have the same information, but in images. As you can see, transport sector is the only sector for whose emissions have never stopped increasing. Aviation is increasing crazily, but also road transportation, which is the one I'm focusing on, has increased like about 20–30%, as you can see here. And so we are improving in all the sectors, but not in transportation sector. And as you can see, there's a huge variability, and all they are increasing quite a lot. And actually, of this increase in transportation sector emissions, the most important sector, subsector, could say, is road transportation, which accounts for a very big share. And within this, of course, you have cars, but also very relevant heavy-duty trucks. So I'm putting this in this picture because actually, yes, I'm focusing on a policy in gasoline taxation, in energy taxation in gasoline and diesel, so in fuel taxation. And this will have some, I mean, our results are having some relevance in this, with this graph, as you will see. So the big challenge here is that if we look at our targets in the sector, we are a bit far away. So looking at the current policies, we are very far from the target, which is a 90% reduction. And as you can see, by 2050, we are very far from that, looking at the current policies. So somehow, we have some instruments in place. At the European level, these are the main instruments having an effect on energy transition in the transportation sector, or in reducing the emissions in the transportation sector. And I'm particularly interested in the emission trading system. Firstly, because as you may know, it's expected to be expanded at the transportation sector by 2026, so we will have a second carbon market in transportation in the European Union. And this will, of course, have some effects, at least in prices, potentially also in emissions. And of course also the Energy Taxation Directive, which somehow limits the minimum taxes across countries, also has an effect. And actually we do know that, right? I mean, we do know that energy taxes, fuel taxation do have an effect in emissions. We know that. Thing is, and this is more, thing is that, of course, what happens in any taxation or carbon market taxation or carbon price is that when you have unilateral policies, what happens with the neighbor country, right? I mean, you may have carbon leakage. Firms may go to the other side of the border where they are not regulated, so this could be a carbon leakage problem in the sense that you reduce their emissions in your country, but they are actually increasing in the other side of the border. Well, this in transportation is just more obvious, right? I mean, if you put carbon taxes in transportation, you might find some carbon leakage here. So this is what we are interested in analyzing here. And actually, we believe this is becoming more relevant in the days today because of policies are, we are ramping up our policies. We need to do a lot of mitigation in the next years. And so we see that actually carbon pricing in the transportation sector is already becoming more popular, right? Including the UTS. Sorry. That piece of information was important, maybe? Yeah, oh yeah. Also relevant, sorry for the typo there, also relevant for the current energy prices, right? Because actually we are seeing that we have all these discounts in all the European countries, like this 20 cents in Spain. This is also relevant in the sense that, okay, how these discounts, once we have an energy crisis as the one we are having today because of the situation in Ukraine, etc. And also before that. So how is this affecting this framework of carbon leakages, etc.? So which is our context? Our context is, of course, that of fuel tourism. Maybe you know these papers of fuel tourism that actually somehow they analyze the cross-border elasticities, right? I mean, this idea of people just filling their tanks in the other side of the border. So if you happen to live close to the border, I mean, you would do that probably, right? Because I mean, if there is a difference in prices, why not, right? I mean, you just would go there and would fill your tank cheaper. And actually, there are many papers documenting this. So we know that there are quite positive cross elasticities in some countries, in some others are not as evident. There is a lag here that I'm not controlling. Oh, yeah. Yeah, so, and actually we also know that beyond the fuel consumption and the emissions related to this, we also know that actually these fuel prices might have an effect even in the car you might purchase, right? I mean, there is also some evidence on that. Yeah. And also we do know that because of the carbon taxes, yeah, we have some information on the carbon taxes in transportation. They do reduce apparently about 8–9%. In Sweden, in British Columbia, some papers already. And these papers also tried to say something on carbon leakage. For Sweden, made no sense because actually there was no point to go to the other side of the border in Sweden because Norway is actually more expensive. So, and actually in Canada, there is some suggestive evidence in this paper and between US and Canada because of the change between exchange between US dollar and Canadian dollar. But the literature that I would like just that I think that frames this investigation better is actually this one, the fuel taxes and the, yeah, that's what I think, and price elasticities. And we do know, actually, this is a very important piece of research for us, that actually we do know that people, consumers, drivers, tend to react more to tax-driven changes than to market price-driven changes. So if the prices increases because of the market, when the fuel prices increase because of the market, people would react to this by lowering their consumption. The thing is that we do know that if these price changes come from taxation, these changes are even higher, right? I mean, people react more to twice or even 4 times, or even 3 times, depending on the paper. But we do know that actually this is happening, right? I mean, that people react more to taxation than to market price changes. And this has been explained that might be because of the permanence of the taxes, because of the salience of the taxes being changed, etc. So our broader research question and now I should move to the main results, and the experiment, is that what if fuel tourism is also more responsive to tax changes? This would be a problem in the current days if we are thinking of this increasing this expansion of the carbon market in the transportation in Europe, etc. Right? So this is somehow our worry, right? So how do we do this? We do a natural experiment. So we exploit an increase in. There was a change in Portugal. There was an increase in the taxes in the excise taxes of Portugal, and we are exploiting this. How this affected this increase in the taxes in fuel in Portugal? How this affected in the other side of the border? So how this affected Spain, right? So this was the impuesto sobre productos petrolíferos, and actually it's important because Spain, it happens that transportation is the main source of emissions and a big share of the external cost. Thank you so much. So let's move very fast, because at the end of the day, this is fast as set. Okay. So now I'm showing like some graphs, but the intuition is very, very fast. So yeah, there was this increase in Portugal, the green line of the taxes. There was not this increase in taxes in Spain. And I'm showing all taxes for gasoline and all taxes for diesel. So I'm exploiting this. And of course, this was somehow captured by the whole evolution of prices. But important mentions here is that you see that there is more difference in gasoline prices between Portugal. So you save more money if you have a gasoline car than if you have a diesel car, right? Crossing the border from Portugal or just filling in Spain instead of Portugal. So this is Spain, and those are the border provinces for those of you. I mean, this is the main comment I always receive. So I show Spain, because otherwise people don't need to know the provinces in Spain. So there you are. We are actually showing this. This is a very long frontier, and so this is a good setting for this experiment, because actually it's the longer uninterrupted border in the European Union. And so this is I'm having like different setting different experiments according to the number of petrol stations they have in the borders. But this is let's move to the results, because at the end of the day I'm showing that this is not important. So this is the evolution of consumption between the treated and the control provinces. Our treated provinces will be just the border provinces. So the other ones are the non-border provinces. So you can see that there is some parallel trends feasible here. And these are the main results. Main message here. We do find an effect on diesel. We do not find an effect on gasoline. So diesel reacts, drivers of diesel react to this. So once the tax increases in Portugal, people start feeling more because of the tax, because they already did. They were already doing, but the thing is, this is capturing the effect of the tax change in Portugal in the petrol station. So they are doing more in diesel, not in gasoline. They just keep the normal. There is some positive effect for the Galician provinces, but I will explain if I have time for this a little bit more. But this is the main thing. And our explanation here is actually, here you have some event estimates for different settings and for different matchings and entropy balances, etc. And results are quite consistent. We do have an effect for diesel, not for gasoline. And then we looked at the synthetic control, right? I'm skipping this, of course. And this allows us to look at the province level and to construct the synthetic the synthetic provinces, and we see that actually Zamora is driving quite a lot of this effect, like 22% increase, and the other one was actually Badajoz. The others were not significant, and why is this? What is our explanation of this? The geographical explanation. Actually, it happens that these two provinces are in the main route from Oporto and Lisboa, and they are the main route from these harbors, from these important harbors to Europe. So our hypothesis here is, or our somehow our mechanism, our explanation of this result is that trucks are reacting to these taxes, whereas drivers are not. Is this important? We think it is, because actually, yeah, thank you, trucks happen to be like 2% of the vehicle fleet, but they have like 20% of the emissions. So this is an important transition you have to do on the one hand, and on the other hand, yeah, we could save a lot of, I mean, this idea of you are having carbon leakage, but also you are having fiscal leakage, I mean, revenue leakage, right? And this is important in terms of this carbon market happening in the next years, because at the frontiers of the European level, this will be relevant, and also within the European Union because of the revenue leakages. This effect happens to be local, as I said, so this is somehow what I already said, so yeah, this is it. Thank you very much for your attention.
Thank you to all speakers for the sharp time that you have devoted. And now it's time for questions, comments, suggestions to the presenters. Okay, just.
A question for Daniel. You said in the title the impact of grid limitations, but you didn't really say about the nature of these grid limitations. Are they the same all the time, or are they between particular regions, or what is the nature of them?
Okay.
Yes, so to Nicola, I was wondering if you could elaborate a bit on the economic rationale for the reduction in volatility, and I think maybe what could be quite interesting is to kind of like have a model explaining some of the mechanisms, because I found it very interesting, the reduction in volatility in your paper. And for Jordi, I was wondering a bit, so what was the control group then? It's other regions of Spain that were unaffected, right? So that's the idea, I suppose. And can you use this also to look at what's happening in Portugal to understand not only the leakage, but like the average effect of the policy, for instance? And also a question is, if it's trucks, so should you extend your analysis to like regions that are a bit more inland, because the trucks then probably travel quite far in Spain?
Sorry, I have a question for Maria. Yes, I'm thinking like whether you, because the data you have basically a very big listed firm, so there will be, but for this kind of firm, there's one issue about the subsidiaries, because there are a lot of subsidiaries across the regions. So I'm thinking that whether these subsidiaries could be considered, because it's possible that the parent firm is not exposed to the regulation, the regional regulation, but many of the subsidiaries are regulated. In that case, it might be like this regional regulation, they might be spill over to other entities, for example, parent firms, by this firm ownership. And in that case, it means that we probably don't need like a national-wide, like even local regulation. They can spread spillover effect to other firms. So I'm thinking whether it could be considered in your data set. Thank you.
Yeah.
Yes, hello, Pablo del Rio from National Research Council of Spain. My question is for Daniel, just for a clarification. You mentioned in your last slide on policy implications, you mentioned as the first one that the inefficiency from redispatching process could be considered when governments set national targets of gas consumption. I was wondering what you meant by these national targets of gas consumption. Yeah, thanks.
I had a question for Jordi. I believe, maybe you have mentioned this in the presentation, but as I understand, the treatment effects were significant for diesel, but when it comes to E95, it was only significant for the Galician states, I believe. Firstly, I wanted to ask if you looked into the reason as to why that is, and if that also was somehow reflected in the diesel in a slightly different way, perhaps. So.
Any other question? No? Just one for Jordi. It's about the, you talk about the specific case, the border between Portugal and Spain, and this relationship could be affected by the landscape, for example, structure. I thinking about the Spain and France, who have the Pyrenees, and it's very difficult to cross that. On Switzerland or Italy, whatever. It could be possible that the landscape produce different effects on that. And for Maria, I have also another question. It's, I don't know if I have misunderstood something, but the increase of emissions when companies implement regional and firm-specific renewable energy policy, is that true? What is the explanation that using both policies, the emissions goes up? Okay.
Okay. Thank you for these questions, briefly. The first one about the relation about grid limitations and the gas consumption. What is happening in Spain and what we also see in the UK is that the need to start some combined cycles to stabilize the system is related to the characteristics of the grid. I have not explained, this is a quite technical problem, but in Spain we have some similarities with the UK. We have low cross-border interconnection, so lower short-circuit current. We have lower voltage support from the foreign countries. So these limitations can be solved with a new ancillary services or installing specific devices in the grids, reactants, capacitors, and that. So we link at the end grid limitations in the way that market provides an output considering a unique bidding zone, but when we try to put in the grid, we find that grid by own limits this why we link that. And regarding your question about, Pablo, the national gas consumption targets, we were referring to when the government should declare to Europe the gas consumption reduction in the scope of the European gas crisis. So Spain should declare that they will reduce the gas consumption. What we say is you should not end just in reducing the amount of consumption or connecting renewables. You should be aware of that inefficiencies. If not, you are not achieving what you expected in the beginning. So this is why we link in the scope of this gas crisis. We are finishing the winter. This paper could be quite more updated several months before, but now in that way. Thank you.
Okay, let's start from the role of subsidiaries and the spillover effect on subsidiaries. I think it is a very interesting topic, and thank you for your suggestion. It is maybe another paper, a suggestion for improve the paper. However, nowadays, in Italy, almost, environmental reporting is compulsory only for larger listed companies. For this reason, I have no data nowadays in order to test also the spillover effect on subsidiary if they are not listed companies. But this is a good suggestion because environmental rules are changing, and maybe also smaller firms could produce environmental reporting. So I collect the data and could test the spillover effect. About the second question on CO2 emissions and regional policies and the policies mix, it is correct. This is a counterintuitive result, but it is exactly as you said. In the case of general policies for reducing air emission, and only in this case, regional policies alone are effective, but the policy mix is not effective. On the contrary, it improves the CO2 emissions, and these are our results.
Thank you. Well, thank you, François, for your question. You really got a good point. At this stage, this paper, which is still undergoing for sure, is, merely speaking, an empirical exercise. We observe a phenomenon, and we try to figure it out, how to explain. Your question goes deeply into the microeconomic action of actors involved. And I think that the answer would be very difficult because we start from an increasing price paid by customers that maybe can influence them to be more conscious in their consumption. So we may imagine to have economic agents impacted by an exogenous factor. So given their utility function, they can change their optimal response. And then it should be studied how, from the micro level of different agents, we have an effect on the aggregation on the meeting of physical demand and supply at a whole different level. So, long story short, I think that going to the rational could be a theoretical effort that I don't want to say is beyond the scope of this paper, but also will require a study completely different. So now what we can say is that given the relevant increase in price that was in the order of magnitude of 20 Australian dollar per megawatt hour was relevant, and so probably most likely customers became more conscious about their choices. But how to detail the transmission is a very difficult point. Sorry, I'm not able to answer better than this. Thanks anyway for pointing out that. Okay, in fact, during the presentation, I stressed out that we are not able to make a causal statement. We are not able to say why it happens and in which direction goes if there exists a causal nexus. At this point, you observe this thing and try to provide information useful for investment decision. Thank you.
Thanks for your questions. François, the control group is the other non-border provinces, and so we believe this is a good counterfactual because actually you see that the consumption is pretty the same. I mean, provinces are pretty homogeneous in that sense in terms of consumption of gasoline, well, right? And yeah, I didn't mention this, but we think it's trucks actually because trucks are only run by diesel. And actually filling the tank it can be like 1,500 liters. I mean, it's like 3,000 euros once one of these guys go to the petrol station. So that's why we think that finding such a strong effect on diesel as compared to gasoline is because of trucks, because they are actually reacting to taxes. Of course, people is still, I mean, one of the co-authors, Xavier, is from Galicia, so he actually knows it. I mean, he says, there's always a lot of people filling up the cars in the borders, right? And yeah, this is continually happening, and somehow we assume this is already part of the very demand of these provinces, and it's parallel trends with the other provinces, only that some of their citizens, some of their consumers happen to be from on the other side of the border. So that's our counterfactual. I'm not sure if I answered your questions.
Something you could check is the size of the roads, because if it's trucks, you would imagine that the petrol stations that are like on small roads would have less of an
Yeah, that's a good point. Actually, that's why we think it comes from the lorries, from the trucks as well, because actually, yeah, you find that those are the main routes. But this is one of the good things, and now I jump to your question of using Portugal and Spain, because actually it's a very permeable frontier as compared to France, where you have the Pyrenees. So this is why actually it's good to use this, right? Because actually this can allow you to not say, okay, it won't happen because of the mountains. No, right? This is the good place to do this. And now I'm jumping to the next question, although it's still related to this, is that why Galician? Why we focus on the Galician provinces? Actually, we do not focus on the Galician provinces. Actually, I didn't mention it, but we have the 3 treatments, and these 3 treatments are only defined in terms of the share of petrol stations they have within the first 25 kilometers of the border. And it happens that in Galicia, 40%, this is Pontevedra and Ourense, they have 40% of their petrol stations within 25 kilometers of the border. So that's why we wanted to see whether this having more petrol stations next to the border is driving the effect. It happens it's not. So it's not driving the effect. So it is some effect, very small effect. We are still checking on this. That's why also we use the synthetic control methods, but we have to admit that here the fits are not as good. Of course, we can improve these fits, but to be comparable with the others, this is something we are working on. But yeah, still we think that that the effect is because it's trucks coming out from the harbors in Lisboa and Oporto going to Europe or the rest of Spain. I think I answered most of it. Thank you.
Okay, thank you very much to the speakers for the brilliant presentation and the audience for good questions. And now we move to the closing session with the second keynote, Juan Pablo Montero. And I think an applause is